my free body diagram of my biological system of a leg extension. So here's my drawing. I got my leg coming down. Yeah, I'm not the best artist, but bear with me. So legs coming down. So this is the weight here. So the force of the weight is force of the arm is 50 Newton meters. The line of action of this bad boy is going to be straight up and down here through this dotted line. Now, if we look at the next point is the axis of rotation right here, which is going to be around the muscles, the insertion points of all those quadricep muscles, hamstring muscles, and then the joint. And then the point of application on the muscle is going to be right in here on the insertion point of those quads and that patellar tendon region. So essentially, this guy's going to kick out, and that's where that point of application is going to be. Now, the line of action for this knee is going to be this way. A little bit angled because it's not necessarily moving in a straight plane there. So then we got 2,000 newtons, and that's going to come in play when we determine our torques over here. So looking at this guy, a few more things to take note here is there's our moment arm, which is 2 centimeters, and that's from the knee here to the line of action upon that knee's moving, and 10 centimeters here from where the knee is to the line of action of the actual weight. So when we take that into consideration, then we go over to our torques. So the torque of the weighted arm is a negative 500 Newton centimeters. Then the torque of the muscle, which is just 2,000 times the 2 there, is going to be 4,000 Newton centimeters. And our total net is going to be a total of 3,500 Newton centimeters. The joint action is going to be flexion, while the muscle action in the quadriceps in that region is going to be a concentric muscle action. So that is the first free body diagram. My next free body diagram is of a non-biological system, and my drawing here is looking like this guy. It's actually a bulldozer, so that's what I decided to go with. Now looking at what we have going on here is I have a rock, and then I have the arm backhoe of the bulldozer bringing that rock straight up. So the force of the rock is right down here. That's going to be 800 newtons, and then the line of action is going to be straight up and down here because we're bringing this rock straight up. So with that being said, our line of action and how a caterpillar works is the power is going to be coming from this joint because these are all going to be locked essentially. So then the line of action is going to be at a cross angle like this with the force being 10,000 newtons, and that's the line of action there. And then our moment arm and the axis of rotation is going to be on the way this joint swivels essentially. So this is our axis of rotation. So our first moment arm I have is 5 meters. Then our second moment arm is going to be from the line of action of the rock movement going straight up and down to the point of application in this mechanical arm, which is right here. That's where most of that stress is going to be put upon. So that's the moment arm is going to be 20 meters there. So then the point of application of the rock is going to be in the bucket right there. That's where that contact's going to be. Now with that being said, this gets our torques. So I have 5 times 10,000, so we have our moment arm of 5. The force is 10,000, so that's going to give us 50,000 Newton meters. And then of the rock, the 20 right here times the 800, that is going to get us the 16,000 Newton meters. And that's going to be a negative direction. The mechanical arm is going to be a positive direction, so that gives us a total net of 34,000 Newton meters. And the machine action would be a flexion status because it's flexing up. That is my second free body diagram of my non-biological system.